Hello and welcome. Today we're going on a journey through time, tracing the fascinating story of ground-penetrating radar, georadar, or simply GPR. Now, you've probably seen military radar in movies and TV shows. You know, those spinning dishes on ships and glowing green computer screens like old-school monitors, but GPR, well, that's military radar's quieter sibling. Instead of scanning the skies for enemies or aircraft, it looks beneath our feet, revealing what lies underground without disturbing the soil at all. Now, in this episode, we'll trace its roots from the chalkboards of the 19th century through the fires of World War II to the icy wilderness of Greenland, and finally to the surface of the moon. Along the way, we'll meet the brilliant and sometimes eccentric inventors who pushed this technology forward. So, buckle in. We're starting not with the machine itself, but with a set of equations thought up by a Scottish physicist in the 1860s. Now, in the middle of the 19th century, some parts of science were, in a bit of a strange place. People knew about electricity, sparks from batteries, or seeing lightning in the sky. And they knew about magnetism, compasses pointing north, or iron filings dancing around magnets. But these two forces seem like separate mysteries. Enter James Clerk Maxwell. He was a quiet, brilliant Scottish physicist. Around the 1860s, he began to suspect that electricity and magnetism were not separate forces at all, but part of the same, deeper system. His work built on Faraday's early experiments, but Maxwell, well, he was a mathematician at heart. He took the scattered experimental results of his day, with many physicists contributed to, and wrote them down as mathematical equations. 4 of them, in fact. Just 4. Today, they're simply called Maxwell's equations. Well, okay, what do they say? In simple terms, they say that an electric field can create a magnetic field, and, well, a magnetic field can create an electric field. So if you let them interact, the result is a self-propagating wave that ripples out through space. Maxwell calculated the speed of these waves, and it matched the exact speed of light. So in that moment, he realized that light itself was a form of electromagnetic wave. Maxwell's discovery was monumental in physics. For the first time, physics joined light, electricity, and magnetism into one elegant theory. But at the time, it was still only a theory. No one had actually seen these invisible waves in the 1860s. That proof took 2 decades to materialize from the German physicist Heinrich Heinz. In the 1880s, Hertz built a spark gap transmitter, a device that sent out bursts of electromagnetic energy. Now, across the room, there was a simple loop of wire that served as a receiver. When the transmitter sparked, the receiver did too, as if invisible ripples had crossed the room. Hertz had just generated and detected electromagnetic waves, what he called Hertzian waves in a humbly physicist way. He also noticed something remarkable, that these waves could bend, refract, or reflect off metal surfaces, just like light. That last property, reflection, would become the foundation of all radar systems, including GPR. At the time, Hertz wasn't thinking about detecting planes in the sky or buried pipes. He was just trying to prove Maxwell right. But his discovery set in motion a chain of innovations that would eventually allow humans to literally see beneath the ground. Now, by the early 20th century, inventors began asking a new set of questions like, could these waves be used to detect something? Well, in 1904, Christian Hüselmeier, a German inventor, created and patented the telemobiloscope. His goal was simple but revolutionary at the time: to prevent ship collisions in fog. His device, mounted on a ship, would send out radio waves that would bounce off anything metal, specifically ships, and it could even sound alarm when something was approaching. It was first patented in 1904, and it was the first radar-like system. The device only detected the presence and direction of ships using the reflected EM waves. It could not measure distance. Although Hüselmeyer's work focused on navigation, it inspired others to look deeper, literally. In 1910, two other German inventors, Gottlieb Leimbach and Heinrich Loewy, patented a continuous wave concept for locating buried objects. Loewy especially envisioned using radar in civil engineering to find underground pipes and hazards without having to excavate. Sound familiar? Their idea was decades ahead of their time. Then, in 1926, Dr. Hülsbeck advanced the technology by proposing the use of radar pulses rather than continuous waves. Now, a pulse radar system could not just measure the presence of a target, but also its distance. And that was the first true step towards depth measurement. And just 3 years later, in 1929, Austrian physicist W. Stern made the leap from lab to field. Using radar to measure the depth of a glacier in the Austrian Alps, Stern achieved the first known practical demonstration of ground-penetrating radar. For the first time, electromagnetic waves were used to map what lay below the surface of the Earth. By the late 1930s, radar technology had become critical to national defense. In 1940, the United States Navy coined the term RADAR, short for radio detection and ranging, right? So not only the ability for us to detect something, but detect its distance from the radar itself. And World War II saw two very different radar systems being developed by the Allies and the Axis powers. And they illustrate a key principle that also applies to GPR, the trade-off between wavelength, range, and resolution. In the UK, they developed the chain home system that operated very low frequencies, about 20 to 30 megahertz, which corresponds to a wavelength of about 10 to 15 meters. This gave this system tremendous range, sometimes over 100 miles, and it was perfect for spotting incoming bombers and squadrons. But the resolution was really poor. An entire squadron appeared as a single blurry echo on their screen. In contrast, Germany developed the Würzburg radar, and it operated around 560 megahertz with a wavelength of about half a meter. It had far better resolution, able to track a single aircraft very precisely, but its range was very limited, only about 30 or 40 miles at most. It was excellent for targeting anti-aircraft guns, but not so good for long-range warning. So this contrast, long wavelengths for range, short wavelengths for resolution, is a lesson still fundamental to all radar and GPR designs today. During the war, radar altimeters were developed to measure aircraft altitude. At the time, they were relying on barometers, and using radar would give them much better accuracy. So over water or flat land, they worked perfectly well. But over Greenland's ice sheets, pilots noticed something strange. Sometimes the radar signal penetrated the ice instead of reflecting off the surface of the ice. And in Greenland, the ice cap could be 3 kilometers thick. The altimeter read that they were much higher than they really were. And that's a dangerous illusion that led to actual crashes. But from those accidents came some insight that radar could indeed see through ice. Now, scientists already realized that radar could map ice thickness, which Stern had already published on in 1929. But by the 1950s and 60s, glaciologists were using radar to measure the depth of ice sheets and glaciers. And that was the first true scientific application of ground-penetrating radar. By the late 60s and early 70s, GPR began moving beyond glaciology. As with most developing technology, military applications further pushed designs in GPR. Now, during the Vietnam conflict, US forces deployed radar to locate tunnels and booby traps placed by the Viet Cong. One of the most significant of these efforts was something called Project Geodar, developed by MIT Lincoln Laboratory under a DARPA sponsorship. It was amongst the first true GPR systems designed to detect tunnels beneath US operating bases. Now, it worked somewhere between 50 and 150 megahertz, and Geodar transmitted nanosecond radar pulses directly into the soil using a sled-mounted antenna. Tests in the US and Vietnam demonstrated its ability to detect tunnel-like voids 2 to 3 meters in diameter at depths of up to 20 feet. That would be impressive today, and it was certainly an extraordinary achievement for its time in the early 1970s. Then came the Apollo missions. On Apollo 17 in 1972, astronauts used a specialized radar, the Lunar Sounder experiment, mounted on the lunar rover. It probed the moon's surface, revealing the depth of the regolith down to kilometers in various subsurface layers. For the first time, radar was used to look below another world. After Apollo, the technology rapidly matured. Geophysical Surveys Systems Incorporated, GSSI as you know them today, was established in 1970. By the mid-1970s, commercial radar systems were appearing everywhere. Engineers used them to find buried pipes and cables, archaeologists used them to locate ancient structures, forensic scientists began applying them to police investigations. The list went on. From Maxwell's equations in the 1860s to practical tools in the 1970s, GPR's journey spanned more than a century of theory, innovation, and exploration, transforming invisible mathematics and equations into one of the most powerful subsurface imaging tools we have today. Ground-penetrating radar is a story of persistence, of scientists and engineers who refused to stop at what they could see. From Maxwell's abstract equations to Hertz's sparks to Hülsemeyer's ship detector, Stern's glacial radar to the warp time, chain home systems to the ice of Greenland, and to the dust on the moon. Every step built upon the last. Today, GPR helps us maintain our cities, preserve our history, and explore new worlds. It reminds us that every invisible wave we sent into the Earth carries with it an echo of more than a century of human curiosity and ingenuity. We'll look at how GPR actually works, the electronics, the antennas, and the invisible ripples that let us peer beneath the surface. Thank you so much, and I hope to see you next time.